Imagine this. The world's most advanced AI systems are running on chips containing billions of transistors. These machines can generate art, write code, and simulate human conversation. Now imagine that some of the mathematical shortcuts behind ultra-fast computation may resemble techniques written down over 3,000 years ago in ancient Sanskrit. Sounds impossible. How could ideas preserved on fragile palm leaves share similarities with the algorithms driving modern artificial intelligence? Is this evidence of forgotten genius, a coincidence? Or are we rediscovering mathematical patterns that humanity has known all along? Today we're exploring, did ancient Vedic thinkers uncover computational principles far ahead of their time? The traditional story of technology begins with modern science, from Newton to Turing, from vacuum tubes to neural networks. But hidden within ancient Indian mathematical traditions is a collection of mental calculation techniques known today as Vedic mathematics. These methods claim to simplify arithmetic through elegant patterns rather than brute force computation. Yet, as computer scientists searched for faster ways to process information, some began noticing something unexpected. Many efficient computational systems rely on the same idea. Break a large problem into smaller patterns, solve them simultaneously, then combine the results. A principle that sounds surprisingly familiar to certain Vedic sutras. Could ancient mathematicians have stumbled upon universal computational shortcuts? Or are we simply recognizing timeless mathematical truths? To understand the mystery, we need to examine one famous sutra, Urdhva Tiryagbhyam. The phrase translates roughly as vertically and crosswise. At first glance, it appears to be a multiplication shortcut, but beneath the surface lies something much deeper. Instead of calculating numbers sequentially, the method processes multiple relationships simultaneously. Visualize lines crossing, products emerging in parallel. Today's chips thrive on parallelism, thousands of operations occurring at the same time. The faster a processor can organize these, the more efficiently it performs. This is why researchers have explored implementations inspired by Urdhva Tiryagbhyam. In specific digital circuits, these designs can reduce computational complexity and improve speed, not because ancient sages invented GPUs, but because efficient mathematical patterns remain efficient no matter the century. The language changed. The principle remained. Now things become even stranger. Artificial intelligence is built on layers, patterns inside patterns, relationships inside relationships, a structure remarkably similar to recursive thinking. One Vedic concept often discussed is ekadikina purvena, meaning by one more than the previous. A deceptively simple rule, yet recursion itself operates on a similar philosophy. Each step builds upon the one before it. Large language models work through repeated transformations. Each stage refines meaning, not unlike a mathematical echo extending through countless levels of abstraction. What ancient mathematicians expressed through sutras, modern AI expresses through matrices. Look closely at nature. Tree branches, snowflakes, galaxies, the same structures repeat at different scales. This phenomenon is known as self-similarity. Ancient Indian geometry often embraced repeating patterns and nested structures. Today, AI systems rely on a surprisingly similar concept: self-attention. Self-attention is the mechanism that powers modern language models. Instead of reading words one by one, attention allows every word to interact with every other word. Patterns emerge across scales, nested meaning. The network continuously searches for relationships, not unlike a fractal expanding infinitely inward and outward at the same time. Both are attempts to understand complexity through patterns. As Moore's law begins to slow, engineers face a harsh reality. We cannot rely forever on simply making transistors smaller. The future belongs to smarter computation, better algorithms, better mathematical shortcuts. And this is where ancient ideas become surprisingly relevant. Not because they contain hidden blueprints for AI, but because they encourage a fundamentally different way of thinking. Compression instead of expansion, elegance instead of brute force, pattern recognition instead of repetition. The lesson isn't that modern science copied the Vedas. The lesson is that powerful ideas can emerge independently across civilizations. Sometimes the oldest questions lead to the newest discoveries. Now imagine the next frontier: quantum computers, self-correcting neural systems, artificial general intelligence. As we move toward that future, humanity may discover that progress is not a straight line. Perhaps innovation is a circle, a journey where ancient insights and modern technology repeatedly converge. Maybe the greatest breakthroughs won't come from inventing entirely new mathematics. Maybe they'll come from recognizing patterns that were always there, waiting, across centuries, across civilizations, hidden in plain sight. So the next time you hear the words ancient mathematics, don't imagine dusty manuscripts forgotten by history. Imagine a conversation, one that began thousands of years ago, about logic, infinity, and intelligence itself. Because whether in the mind of an ancient sage or inside a trillion-parameter AI, the search remains the same: to discover the hidden order beneath chaos. Perhaps that search is humanity's oldest algorithm. Stay with us as we rediscover the future.